All right, so hello everyone, and thank you for joining us today. My name's Devesh, and this is my teammate Rukshana, and we're from TURBO V8, a community-based team in Pleasanton, California. Today we'll walk you through the essentials of getting started with hardware and design in FTC, providing you with practical insights and advice based on our team's experience.
Our goal today is to provide a clear, detailed overview to help you confidently approach the hardware side of FTC. By the end of this session, you'll have a better understanding of the engineering design process, CAD, manufacturing, and common components. Whether you're just starting out or looking to refine your skills, we hope this session equips you with the tools and knowledge you need to build effective robots. Let's dive right in.
Let's kick things off with the engineering design process, which is the backbone of how we at TURBO V8 approach building our robot. It's a structured step-by-step method that helps us tackle challenges in an organized way. Here's how we implement it in our team. Step one is to define the problem. Before we even think about building anything, we take a close look at the game manual. We break the game down into specific tasks, like scoring points by picking up game elements or placing them on a specific target. Then we think about constraints. Are there size limits, weight restrictions, or do we need a mechanism to reach a specific height? This step is critical because it creates a clear goal for our robot.
Next is brainstorming in CAD. As a team, we brainstorm ideas together, focusing on the simplest ways to solve the problems that we've defined. It's easy to get carried away with overly complicated solutions, but simplicity is the key. Once we have a rough idea, we jump into CAD, specifically Onshape, which we'll talk more about later. This is where our ideas become more concrete. CAD allows us to visualize how the parts will fit together, test the range of the motion for joints, and ensure everything will work smoothly once it's built.
From there, we move on to prototyping and testing. This step is all about experimentation. We start with simple prototypes using materials like wood, cardboard, or even old parts we have lying around. The goal here isn't to create a perfect mechanism right away. It's to figure out what works and what doesn't. We test these prototypes rigorously, looking for weaknesses like structural instability or insufficient range of motion. For example, when we were developing our first active intake, we built a prototype out of 3D printed parts first. This allowed us to refine the design before committing to using more expensive materials like aluminum or carbon fiber.
Finally, we arrive at the final implementation. This is where we take everything we've learned from the earlier steps and create a finished version of the mechanism. We use high-quality materials and precision manufacturing techniques, which we will go over in more detail later. At this stage, we also want to think about assembly and maintenance. How easily can the mechanism be repaired or adjusted during a competition?
Throughout the process, we follow a few guiding principles to keep our designs efficient and effective. First, focus on solving the problem in the simplest way possible. Over-engineering may look impressive, but often introduces unnecessary points of failure. Second, test early and often. Iteration is key to success in FTC, and small adjustments can lead to big improvements. Finally, remember that communication within your team is just as important as the design itself. A good design process is collaborative. Everyone's ideas and feedback play a role in building the best robot possible.
Okay, let's move on. Now that we've gone over the engineering design process, let's talk a little bit more about the most powerful tools in FTC hardware, CAD or computer-aided design. For those of you that are new to FTC, CAD might be a little intimidating at first, but it is absolutely essential to creating efficient, high-performing robots. At TURBO V8, CAD has been a game changer for our design process, and here's why. The first and most obvious reason to use CAD is that it allows you to create custom parts. FTC robots are full of unique mechanisms that you won't find in pre-made kits. CAD lets you design parts tailored specifically to your robot's needs, whether it's a custom gearbox, a structural plate, or mounting bracket. This flexibility gives you a competitive edge. You're not limited to what's available off the shelf. We use Onshape, and we highly recommend it for several reasons. First, it's cloud-based, which means that everyone on the team can access the design from any device, anywhere. It's also collaborative, which means that multiple people can work on the same file at the same time. This has been especially helpful to us when deadlines are super tight, as it allows the entire team to contribute without stepping on each other's toes.
Another advantage of CAD is it helps you identify design flaws early. So imagine building an entire robot only to find that one of the arms doesn't have enough clearance to move. Without CAD, you can simulate the range of motion for each mechanism, ensuring everything fits and functions as intended. It's like having a virtual prototype. You can test ideas before spending time and money on manufacturing. CAD can also help with realistic renders, which are surprisingly useful. These renders aren't just pretty pictures. They're valuable for documenting your designs in engineering portfolios, outreach presentations, and even award submissions. A well-documented CAD model can show judges that you put thought into your designing process.
For sure. And if you're just getting started with CAD, don't worry. There are plenty of resources available to help you learn. Onshape, for example, offers a wide range of introductory courses and tutorials. Their platform is very beginner-friendly, and you can find video guides, forums, and even pre-made FTC libraries. Speaking of libraries, the FTC Parts Library is an incredible resource, one that we here on TURBO V8 solely depend on. It includes models of commonly used components like motors, gears, and brackets. This saves you a lot of time because you don't have to create everything from scratch or import everything individually. One of our personal tips is to use what we call the master sketch. It's essentially a top-down view of your robot's layout where you can plan the placement for all of your major components. Think of it like a roadmap for your design. The master sketch helps ensure that everything fits together efficiently, especially when you're working with tight constraints like the FTC size limits. For us, this one tool has saved us countless hours of trial and error.
Finally, CAD isn't just about designing, it's about learning. As you get more comfortable with the tool, you'll start to think like an engineer. You'll learn to visualize these solutions in 3D, consider forces and tolerances, and optimize designs for performance. These skills will not only help you in FTC, but also in future STEM opportunities.
To wrap up this section, CAD is your best friend when it comes to hardware design. It makes your robot more efficient, your designs more reliable, and your entire process more professional. Don't be afraid to dive in and start experimenting. The more you practice, the better you'll get, and the more you'll see how transformative CAD can be for your team.
Once you finalize your CAD designs, the next step is to bring them to life through manufacturing. This is where all the hard work you put into design starts to take shape. At TURBO V8, we've experimented with a range of manufacturing techniques and vendors to create parts that are both precise and durable. Let's walk through the key options for custom manufacturing and how to make the most of them. The first thing to consider is the materials you'll use. For most FTC robots, you'll want a mix of lightweight and strong materials. Here are a few examples. Polycarb is a popular choice for plates because it's lightweight, flexible, and impact resistant. Aluminum is also fantastic for structural parts because it's strong yet relatively light. Carbon fiber is another great opportunity for its rigidity and weight savings, but it can be a bit more expensive. For prototypes, materials like wood and 3D printed plastics like ABS, PETG, or PLA are cost-effective and quick to produce.
When it comes to manufacturing these materials, you have several options. For CNC machining, which is great for cutting precise shapes out of metal or polycarb, we recommend vendors like Sen or Fabworks. For 3D printing, there are plenty of materials and printers to choose from. We typically use PLA or PETG for quick prototypes and carbon fiber PLA for stronger parts. If your team doesn't own a 3D printer, there are always services like CNC Madness or local makerspaces that can print your designs for you.
Once your parts are ready, you'll need hardware components to assemble your robot. This is where vendors come in. Over the years, we've built a list of trusted sources that provide reliable, high-quality components. GoBuilda is our go-to for most FTC parts. They offer wheels, motors, servos, and starter kits, and their components are super reliable. They recently released new electronics like the Servo Commander and odometry pods, which make wiring really easy for your complex mechanisms. Swiss Robotics is another great vendor for pre-assembled kits, sensors, and wiring tools. For specialized motors and servos, Melon Robotics is excellent, especially if you need their Hall effect encoders. Misumi is also one of our favorites for linear slide extensions because they're incredibly precise.
Another vendor we can't recommend enough is McMaster Car. They're unbeatable for fast shipping and have a huge variety of parts, especially if you're in Northern California. Whether you need bearings, surgical tubing, or even the most random of tools, they always got you covered. And of course, there's Amazon, which is perfect for last-minute needs. You'd be surprised at how many random FTC essentials like zip ties and heat shrink tubing you can find there.
A quick tip here, when sourcing parts, always consider lead times. Some vendors like McMaster Car ship almost instantly, but others may take weeks, especially for custom orders. Plan ahead and to avoid delays. At TURBO, we try to map out our build schedule and prioritize ordering critical parts early in the season.
One thing we want to emphasize is that custom manufacturing doesn't always have to be expensive or overwhelming. Start small. For instance, you don't need a fancy CNC machine to make effective parts. We don't use one. Well, we don't have one. You can use hand tools to cut polycarbonate or rely on 3D printed parts for lightweight mechanisms. As you gain experience, you can explore more advanced techniques like CNC machining or laser cutting.
Ultimately, custom manufacturing gives your team the flexibility to build exactly what you need. Instead of being limited by off-the-shelf parts, it's one of the most rewarding aspects of FTC hardware because you get to see your design go from concept to reality. And by working with reliable vendors, you can ensure that the parts you create are competition ready.
To wrap things up, let's remember these three things. Choose the right material for the job. Lightweight when possible, durable when needed. Always use trusted vendors to save time and ensure quality. Also, remember to start simple and scale up your manufacturing techniques as your team grows. With the right approach to custom manufacturing, you can be amazed at what your team can build.
Now that we've talked about manufacturing and sourcing parts, let's shift our focus to some of the common components you'll encounter when designing an FTC robot. Every robot has key systems that make it functional, things like drivetrains, intakes, and scoring mechanisms. We'll break down these components and share some of our tips to help you design them effectively. Let's start with the drivetrain, which is the foundation for every robot. The drivetrain determines how your robot moves, and there are several types to choose from. One of the most popular in FTC is the mechanism drivetrain, which uses mechanism wheels to allow for omnidirectional movement. This means your robot can move sideways, diagonally, or even spin on the spot. It's incredibly versatile for navigating tight spaces or aligning with field elements. Quick tip here is to use belts instead of gears in your drivetrain wherever possible, because belts reduce backlash and improves your precision, which makes your robot easier to control. If you're just starting out, you can also use custom commercial off-the-shelf drivetrains like those available from GoBuilda or Swift Robotics. These kits are pre-designed and easy to assemble, so you can focus on building other parts of your robot.
Next up, we have our intake system, which is used to collect and control game elements. A good intake should be fast, reliable, and lightweight. When designing an intake, it's good to aim for minimal friction and keep all moving parts as light as possible. For example, at TURBO V8, we found that using bare motors with high RPM works really well for picking up objects quickly. Our intake uses spinning rollers and belts to grab and lift game elements. Make sure to prototype your intake early in the season. This will help you determine the best materials and configurations. For example, in our previous season, we experimented with many different types of rollers, like foam and rubber, to find out what worked best for the game pieces.
Robots that need to extend or reach, linear extension systems are key. They're often used for mechanisms like arms. When designing a linear extension, prioritize stability and smooth motion. Grease your slides to reduce friction and add hard stops to prevent overextension. One issue we've run into before is sagging in the slides, which can happen if the materials aren't strong enough. To avoid this, choose high-quality slides like those from Misumi or GoBuilda. Another important aspect is dust and debris management. Over time, they can interfere with your slide's performance, so a simple solution is to use protective covers or clean the slides regularly.
Once you've collected game elements, you need to find a way to deposit them, and that's where end effectors like claws, buckets, or turrets come in. For a claw mechanism, make sure that the arms are compliant enough to grip the game pieces securely without damaging them. Keep the claw as light as possible, especially if it's mounted on an arm or side, because every gram adds strain to your motors. That's torque. If you're using a turret, which provides 360-degree motion, design it to be as simple as possible. Turrets can add a lot of flexibility to your robot's scoring capabilities, but they're also complex to build and more complex to control.
Let's not forget about the transfer mechanisms, which move game elements from one part of the robot to another. For example, if your intake collects elements at the bottom, but your scoring mechanism is mounted higher up, you'll need a transfer system that uses belts, linkages, or lifts. One tip here is to use hard stops to ensure that the mechanism reaches consistent positions. This makes life much easier for your software team because they can program accurate movements without relying solely on sensors. Speaking of sensors, adding them to your robot can dramatically improve performance. For example, encoders and distance sensors can enhance precision during autonomous mode, while color sensors can help identify game pieces. Sensors can also provide feedback to drivers, which is invaluable when visibility is limited during teleop.
To summarize this section, here are the key takeaways for designing common components. Drivetrains. For drivetrains, always remember to use belts to reduce backlash as much as possible and consider mechanism wheels for an omnidirectional movement. For intake, make sure to keep them lightweight and test different materials very early in the season. For linear extensions, make sure to prioritize stability, use high-quality slides, and make sure to add hard stops. For end effectors, design your claws or turrets to be simple, lightweight, and effective. For transfer mechanisms, use hard stops and sensors once more to improve reliability and driver control. With a good understanding of these components, you'll be able to build a robot that's both functional and competitive.
That wraps up our overview for common components. Remember, the key to success is iteration. Don't be afraid to test, fail, and improve. Each mechanism you build is a learning opportunity, and with time, you'll get better designing and optimizing these systems.
Thank you for joining us today. We hope this session has given you a solid foundation for getting started with hardware and design in FTC. Whether you're building your first robot or looking to refine your existing designs, we encourage you to experiment, learn, and grow with each build season.
Remember, success in robotics is all about iteration and teamwork. Start simple, prototype often, and don't be afraid to learn from your mistakes. With practice, you'll be designing and building amazing robots in no time. Good luck, and feel free to reach out if you have any questions or need advice. The FTC community is here to support you in every step of the way. So yep, that wraps up our presentation. Thank you for listening.
Thank you for joining us. I have a question regarding your presentation.
Yep.
Okay, so my question for you is, like, can you share an example of a hardware implementation that didn't work maybe as planned, and how did you improve it?
So I'll take this one. Early in the season, we realized that trying to use an active intake was probably the most viable strategy to picking up blocks consistently from the submersible, especially because they're randomized and it's really hard to see inside the submersible from where the driver is standing. So we focused most of our hardware resources to designing intake prototypes. We experimented with a lot of different kinds of intake designs. We started ones that focus on taking in blocks in their wide orientation. We tried some that used angled ramps. We tried ones that don't have ramps. We used gecko wheels, we used sweepers, we used rubber grips on our sweepers to try to improve efficiency. And eventually, through all of this fine-tuning and iteration, we came down to a solution that works pretty effectively during competition. Right now, our final intake design features a capsule that intakes the blocks in their long form orientation, has a counter roller at the bottom, and surgical tubing sweepers at the top that are powered by a bare motor, so you get maximum efficiency and speed while keeping it light.
Thank you.
Yep.
I also have a question. How do you approach adapting hardware designs to new game challenges each season?
So just could you repeat your question again?
How do you approach adapting hardware designs to new game challenges each season?
Right. So as we mentioned earlier in our presentation, the first step to approaching any season is going through the game manual. At the start of our season, on the day of kickoff, we had a team meeting where we kind of projected our game manual onto the TV screen. We read through everything, all the pages that we read before, all the pages that were new, read through each and every instruction to see what are the nuances of the game. Obviously, through the game trailer, you can see what the game requires you to do. This season is pick up blocks, deposit them in baskets, or hang them on the specimen rack. But every season has its own complexities. For example, hang. There were so many questions about what is the right and optimal way to hang and like what's considered legal, what's considered illegal. And these are the kind of nuances that you can actually read from the game manual and understand, which gives you a leg up early in the season because you don't have to wait for Q&A to come in and answer these questions for you. You kind of just have a layout. Once you're done with that, then obviously the first step is go to the whiteboard, right? Go to the whiteboard, start drawing random lines, try to see what you've done before in the past and see how you can implement it with the current season. For example, a lot of the robots this year seem very close to center stage robots. Most of them feature vertical extensions with horizontal extensions paired with an active intake and some kind of transfer. And then this time we use claws, last season we used buckets, but it's more or less the same. Because we had that leg up, because we played in center stage, we were able to effectively prototype and come up with strategies to approach the season early on.
Thanks.
I also have a question.
Mhm.
So what were the biggest challenges that you got when you first learned like CAD and construction, like robot construction?
So for me, I actually only recently joined FTC about like a year ago. So for me personally, as far as CAD goes, I had my first experience during the summer where I was tasked to build an entire robot by myself. So that was definitely a very interesting experience. But something I would recommend is take one step at a time. Have one mechanism that you'd like to focus on per like each iteration. And for example, take like an active intake. Just choose an active intake, maybe from a past game, or copy it down, maybe make some modifications of your own, and make sure you understand how the model works. And that's obviously like allows you to get more practice in. And for something like CAD, which is a lot of repetition most of the time, practice really does make perfect.
I think to add on to that, when I started, my first season was Power Play, so about 3 years ago. When I joined the team, I didn't really know much about hardware implementation, CAD, or any of the sort in general. But moving forward, the first thing that I was tasked to make was an active intake. That active intake was iterated upon like 8 to 9 times throughout the season just to get perfect. And that's the kind of practice that you really need to use in order to get really good at CAD. It's this iteration through the design process that allows you to fine tune your designs and really get efficient robots.
And like we said, there's many tutorials online if you're trying to get into CAD. Onshape itself has like a very large YouTube playlist that you can follow through. There's always other courses as well. So I encourage you to look into that.
Okay, thank you so much.
Thank you.
I think I saw a raised hand earlier.
That was me. I was wondering, what kind of sensor do you recommend the most? Like, when aside from the encoders, which we've used in our robot as well for our team, but would you rather be using like color sensors to figure out like that you're holding the right block during the autonomous period, or would you rather be using something that like looks around at the April tags and whatnot? Like, what would you recommend the most?
So when it comes to sensor implementation, right, that's really more of a game preference. This season, we didn't find anything that required you to park in random locations. That was an element that was part of previous seasons. So we solely relied on cameras for that one. We would look at the randomized game element and then read the April tag on that one and then go park in the right location. For this season, there's nothing like that. You can start wherever, park wherever. So they made that pretty easy. I wouldn't recommend reading the April tags on the field walls because those are usually inconsistent depending on where you're playing. Sometimes field construction can be a little finicky. They have that plus or minus 1 inch tolerance, which can really affect the performance of your robot depending on how much you rely on these April tags. But I do completely recommend using color sensors to intake blocks from the submersible because they can give you really useful driver feedback. If you're positioned in a spot where you can only see the pillar of the submersible, but you want to know what block you received, you can configure it such that when you get the right block, your controller starts vibrating, your latch mechanism on your intake seals up, and your robot automatically transfers. Using these sensors allows you to automate most of your autonomous processes, which increases efficiency during the game.
Thank you.